2-1, integers and rational numbers. First, let's talk about numbers we've always used for a while now. Whole numbers. Whole numbers start with 0 and go up. 0, 1, 2, 3, 4, so on and so forth. Negative integers start with -1 and go to -2, -3, -4. It's all the negative whole numbers. Positive integers start with 1, 2, 3, 4. Now look at those three sets of numbers. There's one number that only one of them has. Which one? 0. 0 is a whole number, but it's not a negative integer and it's not a positive integer. It's just in its own category by itself. A number is rational if it can be written in a fraction, a over b, where b is not equal to 0. So, let's ask some questions. Is 5 a rational number? Can I write it as 5 over 1? Yes, so it's rational. Is -7 a rational number? Yes, because it can be written -7 over 1. Is 1/2 a rational number? Yes, because it's already in that form. Is 0.5 a rational number? Yes, because that's the same as 1/2. Okay, these numbers, are they rational numbers? Yes. 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 All of these are rational numbers. Okay, now we're going to classify some numbers. Is 5 a whole number? Yes. Is 5 an integer? Yes. Is 5 rational? Yes. Is -2 2/3 a whole number? No. Is it an integer? No. Is it rational? Yes. Is 0.6 a whole number? No. Is it an integer? No. Is it rational? Yes. Okay, here's some more. -24. Is that a whole number? No. Whole numbers start at 0 and go 1, 2, 3, 4, 5, 6, 7, 8, like that. Is it an integer? Yes. Is it rational? Yes. 2.7. Is that whole? No. Is it an integer? No. Is it rational? Yes. 42 over 5. Whole? No. Integer? No. Rational? Yes. 800. Whole? Yes. Integer? Yes. Rational? Yes. Okay, this is example 3, page 65, talking about stars. Apparently, a star's color index is a measure of the temperature of the star. The greater the color index, the cooler the star. Order the stars in the table from hottest to coolest. So here's the stars and their values from the table. There's only 4 of them. Write those down on a piece of paper, and then we're going to put them in order. Now we have to take these numbers that went with these stars and figure out where they go on the number line. Okay, notice this number line does not have 1, 2, 3. It has 0.1, 0.2, and 0.3. and -0.1, -0.2, and -0.3. So, you can label your number line like that. You don't have to go with whole numbers. Now we've got to fit those on there. So, the first study hall. So, back to what I was trying to say, we have to put -0.03 on to this chart. Okay? Where does -0.03 go? It goes around right here. Okay, that is approximately where -0.03 would go. Where does -0.22 live? Approximately right here. That's where that would live. Where would 0.09 go? Well, 0.09 would go right here. Where would 0.21 go? 0.21 would go right here. Now, here's how I can tell where they go, because this is a little difficult. Well, if I took this 0.2 and went 0.20, wouldn't it make sense that 0.21 would be right there? And if I took the 0.1 and went, oh, that's the same as 0.10, wouldn't it make sense that 0.09 would come a little before it? Now, it's harder in negative land, you know, because negative land is sort of like backwards. So, if this is negative 0.10, would negative 0.03 be right around there? And then if this one was negative 0.20, 0.20, wouldn't negative 22 be a little past it, closer to the 3? This is sort of hard to think through, so you may have to spend some time looking at example 3 so you can understand it. Okay? Now, it said in the problem that the greater the color index, the cooler the star. And then it asked us to arrange them from hottest to coolest. Well, our answer is not going to be the numbers. These numbers are in order now. All of these numbers are in order, but you have to go back and put the star's name with them. So, this was the star that started with an S. I'm assuming that's Shala. This one was Rigel. This one was Dinobola. And this one was Arneb. So your actual answer would be the names of the stars in the correct order. When you're putting numbers in order, it's much easier if they're in the same form. Well, obviously these are some fractions, some decimals, some whole numbers. So you're either going to have to choose to put them all as decimals or all as fractions. Since you have a calculator in your hand, I would change them all to decimals. So that would be negative 3. 1/5 is 0.2 as a decimal. That's already a decimal. And 7.5 is 7.5. Now, obviously, negative 3 is the smallest because it's the only negative. So it's going to come first. To see where the other ones go, let's think logically. 0.2 is a part of a number. It's part of 1. It doesn't have 5 holes or 7 holes, so it comes next. Okay? 5 and part would come next. 7 and part would come next. So this one was already in order. Sometimes that happens. Okay, opposites. The opposite of negative 6 is 6. The opposite of 7 is negative 7. But you need to think algebraically. So, when it says if some number A equals negative 2.5, then the opposite of A would be negative A. That's the opposite, right? That would equal the negative of negative 2.5, which is 2.5. So it's really saying the same thing. It's saying this and this are opposites. But the way they're saying it is sort of a different kind of way you're not used to with algebra. That's saying if A is this, then negative A is this. So you need to understand what that's meaning. Okay, absolute value means how far from 0. So, remember, these lines are saying take the absolute value of this number. How many spaces is it from 0? Well, it's 2. Absolute value of negative 2 is also 2. It's 2 spaces from 0. Absolute value of 0 is 0. There is no positive or negative 0. 0 is just 0. Now that's the basic way you learned it before. Now you have to learn it in an algebraic way that's a little bit different. Okay, if A is positive, then the absolute value of A is A. So let's think of some examples of that. If A was positive, it could be positive 2. The absolute value of positive 2 is 2. If A is positive, it could be 3. The absolute value of 3 is 3. Here's the second one. If A is 0, then the absolute value of A is 0. That one only has one example. Absolute value of 0 equals 0. Okay, here's the third part. If A is negative, then the absolute value of A equals negative A. Now this one's weird. That's really not saying negative A, it's saying the opposite of A. So check this out. Absolute value of negative 3, that is 3. Isn't 3 the opposite of negative 3?
Okay, let's stack them.
Okay, now that I've thoroughly confused you, because this is a little confusing at first, this thinking algebraically, let's try to put all of these rules together with some problems and see how that works. Okay, here we go. Absolute value of 5. That's a positive number, so it's just 5. That's how this rule is working. Okay? Absolute value of negative 3. It's negative, so it's the opposite of negative 3, which is 3. If the absolute value, what's the absolute value of 0? Well, if A is 0, the absolute value is 0. That's logical anyway. The weird rule is this rule, because when you see A and negative A, you think this answer is going to be negative. It's saying, if A is a negative number already, then take the opposite. This is the way they say the opposite in algebra. The opposite of A is negative A. So the opposite of negative 3 is 3. Okay, let's do this one. If A is negative, it's negative. It's going to be the opposite. Opposite of that is 85. Whoops. Okay. 6. Absolute value of 6. How far? It's 6. It's positive, so it's going to be 6. Okay, easier than you thought. Difficult to explain. This is found on page 66 of your book. You need to check this out. Anytime your book has a little blue thing that looks like a notebook that says key concept, it's usually important. They're going to use it over and over and over again. Conditional statements. Conditional statements. This is found on page 66 if you have your book. Conditional statements. Okay. This is a statement that has two parts. It has a hypothesis and a conclusion. Hypothesis, conclusion. The ones we're going to look at today, the type of conditional statement we're going to look at are called if-then statements. Okay? The if part contains the hypothesis. The then part contains the conclusion. Let me read you one and listen for the if and the then. Hypothesis, conclusion. If A is a positive number, then the absolute value of A equals A. Which part is the hypothesis? The part that said if A is a positive number. The conclusion comes after the then. A, absolute value of A equals A. Okay? Listen again. If A is a positive number, then the absolute value of A equals A. Now, in math, an if-then statement could be true or it could be false. Some of them are true, some of them are false. If it's false, for just one example, if you can find just one place where it's false, that is called a counterexample. A counterexample is what you use to prove if something is true or false. Let me show you how it works. Okay, here is an if-then statement. How do I know it's an if-then statement? Because it says if-then. If-then statements. Okay, which part is the hypothesis? This part. The part after the if. Which part is the conclusion? This part. The part after the then. Two parts, hypothesis, conclusion, if, then. Now, the question is this true? Some if-then statements are true, some are false. If it's false, you have to be able to prove it's false by a counterexample, an example that would show that this doesn't work. But this says, if a number is an integer, then it could be positive, negative, or 0. Well, there's some positive integers like 1, 2, 3, 4, and so on. There's some negative integers like negative 1, negative 2, negative 3, and a bunch more. And there's 0. So is there any other thing you can think of that would prove this false? Because all of these prove it true. No, this is a true statement. Let me show you an example. Okay, if a number is an integer, then it is positive or negative. Okay, this is an if-then statement. If, then. Hypothesis, a number is an integer. Conclusion, it's positive or negative. Is this true or false? It's false. Here's why it's false. There's a counterexample. What about 0? 0 is an integer, but it's not positive and it's not negative. It's just 0. So one counterexample proves that this is false. To prove it false, you must have a counterexample. Okay, here's another one. If a number is a rational number, then the number is positive. If, then. An if-then statement. So, here's the hypothesis. If a number is rational, here's the conclusion. Then the number is positive. Can you think of any rational numbers that are not positive? Because I can. How about negative 4? That's rational. It's not positive. How about negative 1/2? How about negative 0.06? All of those are rational, but they're not positive. So that means this if-then statement is also false. I just need one counterexample to show that it's false. Video homework. Woohoo! Get it done. Have a good evening.